I'm really, really pleased to be here with you for the winter event. As Chris very kindly introduced me, my name is Anna Ploszajski. I'm a materials scientist, as you were expecting today. So today I'm going to be talking to you about what materials science is, what we do as materials scientists, and then looking at one particular material, the material of paper today, and thinking about how we can link those materials properties to making things, because materials science is a wonderful subject that has lots and lots of crossovers with other subjects, and I'll talk a little bit about that later. But first, I wanted to tell you a bit about what materials science is and what we do as materials scientists. So, like Chris said, materials science is the study of stuff. So we look at metals, plastics, ceramics, glasses, natural materials like wood. And what we do is we use science to zoom in really close so that we can look at atoms inside materials. So we use things like microscopes and very high powered instruments to have a look inside. And we're looking for atoms. And we're looking to see what types of atoms those are, like off the periodic table that you will have learned about in chemistry. And we're looking at how they arrange themselves inside those materials, because the way that atoms arrange themselves inside materials and the strength of the bonding in between those atoms is all of what controls the materials properties that we experience of materials in our everyday lives. So it's all to do with the atoms and the strength of the bonds in between atoms in steel that makes steel hard and strong and tough and can conduct electricity and all the materials properties that we know of steel. Exactly the same can be said for a material like jelly, right? The atoms inside jelly are arranged in such a way and are bonded in such a way that jelly is wobbly and delicious when you eat it. All of this boils down to atoms inside materials. So we use science to look at those, but it's also very tied into engineering, because materials make up the world around us, as we know. And so what a job of a materials engineer is to understand how science sort of controls materials properties, and then use that science to either choose the best material for a certain job. So to choose the best type of steel to build a bridge out of, or the best type of rubber to make a tire out of. Or we can just discover and invent entirely new materials in the lab. And throughout my career, I've done a little bit of both of those things as well. So that's broadly what materials science is. And so today what we're going to be doing, as I said, is taking a look at one particular material, the material of paper, and taking a materials science approach to understand what it is, what it's made up of, and how what it's made up of dictates its materials properties. And then we're going to be exploiting those materials properties with a making task. So what I'd like you to do is to have to hand during this session 2 pieces of paper. I'll give you a couple of seconds to grab some of those. They can be any size as long as they're not tiny. I don't want a post-it note, but like an A4 piece of paper or an A5 notebook or something, anything like that is fine. But I want 2 pieces of paper. And what we're going to be doing, as I said, is having a look at the material of paper, because it's an everyday material that we don't really often think about, do we? You know, it's so easy to come by. It's everywhere. It's in packaging, it's in books, it's in classrooms, it's on walls. You know, we use it all the time, and so we don't often actually think about the science behind it, but there is a lot of really cool science which we'll be exploring together today. So hopefully you've now got your 2 pieces of paper, and first of all, what I want you to do is be a bit of a material scientist about it. Hold up your piece of paper and really look at it. And I know that sounds like a bit of a mad thing to do, but really have a look at that paper, right? Notice how thin it is. Notice the sound that it makes. Notice that when you pick it up, sometimes it creases, right? It's not as pristine as it was before you picked it up. It's very flat. It's probably quite sort of blank unless you've actually written on it already. But that's a good point as well. You know, paper is a material that is made for writing on, right? We've made it throughout history, and I'll talk about the history of paper later, but we've made it so that we can put marks on it and communicate on paper. But we're not going to be doing that yet. All I want you to do is to kind of think about the paper, think about what it is, and see if you can zoom in with your eyes, like a material scientist, zoom in and have a look at what the surface of that paper looks like. you might think that it's just a completely blank sheet, but once you zoom in a little bit, you can start to see a kind of texture to it. It's not actually as flat as you think. There are probably some sort of ridges. It's a little bit textured on there, depending on the type of paper that you are holding. And what I'd like you to do next is just to rip a corner of your piece of paper and have a look at that. In material science, we would call that a fracture surface, right? A surface that is created after a material breaks. And you're going to be hearing a lot about broken materials later. But take a look at your ripped paper surface. And what you'll probably see is little sort of fibers. I'll try and hold mine up to the screen. You can see that a bit there is sort of more see-through. That's kind of half of the width of the paper. And you'll be able to see fibers at that fracture surface. And those are the fibers that make up paper. Because paper is a substance that's made out of a material called cellulose, and it's made of cellulose fibers. That cellulose comes from generally kind of plants. Today, most of our paper cellulose comes from wood. Previously, it would have come from sort of cotton and cotton rags in history. But these days we make paper out of wood. And the way they do it is to kind of get the wood, they shred it up very, very finely, so fine that the wood becomes these little tiny, tiny fibers. And they then disperse those fibers in water, lift them onto molds, and create very thin sheets of paper. So we can see those fibers in there. I'm going to show you with my close-up camera. We're going to zoom in even further, which is what material scientists love to do. I haven't got an electron microscope in my kitchen, unfortunately. Maybe one day. But here's my close-up camera, which will show you a little bit more detail about what we're looking at here. So if I put that on there for you and focus on the edge of that paper, adjusting the focus, you can see there are lots and lots of little fibers, which is probably the sort of stuff that you would have been able to see on your piece of paper as well. So you can see that paper is made up of fibers. I've got a couple of other types of paper to show you here, because I just love microscopes so much. So I want to look at microscopes all day. This is a piece of paper from a kind of dishwasher tablet cardboard. So you can see the kind of corrugated cardboard there. You can see the fibers again. But also within there, this is kind of a brown piece of cardboard, but you can see very, very tiny flecks of colored particles in this cardboard, can't you? Here's a bit more of the rippy bit. So you can see more of those fibers. They're kind of tangled in there. And there's these little blue and black flecks, aren't there, in this material? And that indicates to me that this cardboard has been made out of recycled paper, because recycled paper is a kind of jumble of all of the old stuff that we've thrown away. They've sort of shredded it up so that those fibers are back in that watery solution again, and then recast it as a new piece of paper. But they can't clean all of the inks and all of the kind of text that has been printed onto this material. So it just remains in there. So recycled cardboard often ends up as being this sort of brown mixture of lots of different colors of paper. I've also got an egg box to show you. This is paper. This is more like cardboard, really, but it's a really nice example of, again, you can see that's the printed ink on there, but you can see these little flecks of sort of old recycled material. And yeah, if you look at the edge, sort of very, very fibrous as well. Those little cellulose fibers in there, which have made up that cardboard. So there you have it. Paper is made up of fibers. It's made up of cellulose. And if I show you the molecule of cellulose, it can help to describe exactly why paper is the way that it is, because I said to you, that's what material scientists are all about. So I'm sharing this picture here with you. This is molecules of cellulose all bonded together. So this is what the atomic structure of one of those little fibers would look like if you were to zoom in way, way more than I have just done with my little microscope. If you were to zoom in with an atomic microscope, with an electron microscope, and then even further than even an electron microscope can do, this is what you would see roughly. You would see all of these different types of atoms. You'd see hydrogen atoms, oxygen atoms, and they're all carbon atoms, all bonded in these little rings in this kind of grid-like structure. Now, this is what cellulose looks like. So I want to show you a couple of things. The first is that there are lots of strong bonds in between the oxygens and the carbons and the hydrogens in this diagram here, in the cellulose molecule. But there are also some slightly weaker bonds in there as well. If you look closely, some of the bonds on here are drawn with a dotted line rather than a big, thick line. And those dotted lines indicate a weaker bond. These are called hydrogen bonds, and they are bonds between hydrogen and other atoms in the structure. And these hydrogen bonds are very weak. When you just ripped your piece of paper, you were ripping lots of hydrogen bonds there. You were also, those hydrogen bonds can also be broken by water. So if you were to put your piece of paper in water and soak it overnight, those hydrogen bonds would get broken by the water molecules. And so your paper would kind of disintegrate. And so we know that paper and water doesn't mix very well. And that is why, is because water molecules can infiltrate into the paper and break those hydrogen bonds, which is what is holding the material together. There's also other things that we can do to paper apart from ripping it, which changes these hydrogen bonds as well. So what I want you to do next is, I'll just stop sharing this. What I want you to do next is to take a second piece of paper. Well, actually take your first piece of paper again, and just fold it in half, or fold a little corner of it. Okay, like that. And that's a property of paper that we really take for granted, the fact you can fold it, right? We do that all the time. We fold cards, we fold envelopes, we fold pieces of paper in half all the time in our pockets. We fold receipts, we scrumple things up. But this is actually a really useful property of the material of paper. And what's happening here at a kind of molecular level is that when you fold that paper, all of those little fibers that we've seen, ordinarily they form this kind of tangled mat like we saw under the microscope. But when you fold the paper, you break the bonds between some of those fibers, and you also snap some of those fibers in half. So you damage the paper in a way at a kind of at the level of the fibers. And you also can break some of those hydrogen bonds as well, simply by bending the paper, by creasing the paper. And so if you uncrease your paper again, try and make it flat, it will never go back to how it was again. That's an irreversible material process, folding a piece of paper, because you've broken some of those fibers and you've broken some of those bonds at the smallest level. And so this paper is never going to be the same again. It's always going to remember what you did to it. It's always going to remember that little crease. And so, like I say, as material scientists, what we do is we try and understand what's going on at the atomic level and work out why materials behave like they do. So we can explain why a piece of paper can never be uncreased using material science. And then what we can do is to use that knowledge of what happens to a piece of paper when you crease it to our advantage, to make new things, or to make things and to choose the best material for the job. So that's what we're going to be doing next. With our second piece of paper, we're going to be making something together. So what I'd like you to do is to take your second pristine piece of paper, like so, and it needs to be a square for this make. So don't worry if you haven't got any scissors, we can do it with just ripping, because again, paper is an excellent material for ripping. So take your piece of paper. If it's not already a square, then fold a corner of it diagonally up. Hang on, I'll just show you this. Fold a corner across diagonally like that, so that the short edge of the paper, if it's A4, meets the bottom edge like that. So you've got a right angled triangle here. And what I want you to do is just to then bend that extra bit round, crease it, and then rip it. And that's another interesting thing, isn't it, about the fact that you're breaking those hydrogen bonds inside that material. Because when you crease a piece of paper, like we said, you're damaging those fibers slightly. So if you wanted to then rip that piece of paper, those sort of that damaged area, that damaged fold is going to be the weakest point through which you can then rip the paper. So I've got my flap here. There's the paper as it was. We've folded it over like that. And then we've got this little bit at the top, which we need to rip off. So I've just folded it there. I've scored it quite closely with my fingernail, and I'm going to rip it like that. So now I've got a right angle triangle here, a blank piece of paper there, which we can just discard. And what we've ended up with is a square. And that's what I want. So we've got a square and we've got one fold through the middle. If you already had a square, I want you now to fold your paper diagonally across like that and then unfold it so you've got a square. And the next step is to turn it 45 degrees and fold it in the same way so that you've got two diagonal folds on your square piece of paper. Like so. So we've got sort of two diagonal folds. And next, what I want you to do is to take each corner and fold that corner into the middle, like that. So align this corner into the middle of your square. Like so. So you should have a flap like that. And I'd like you to repeat that 3 more times so that you've got each of your corners folded into the middle. Like so. So that's how it was before. And each of your corners has been folded like that into the middle. Okay. Once you've done that, I want you to turn it over so that you've got your sort of flat side. Oh, and I want you to do exactly the same thing. So take the new corner and fold it into the middle. This needs to be the side that hasn't got all of your previous corners on the back. So turn it over and then fold on the other side now, each corner into the middle of the square. Okay. And then once you've done that, so these are the ones that we just did. Once you've done that, I want you to fold your square over in half that way. Oops. And make a nice crease there. So these are the flaps that we just did, over in half that way. And then open it out. Turn it 90 degrees and fold it in the same way so that we've got another nice crease there. Okay. So now what you should have is something that looks a little bit like this. We've got our second corners folded into the middle. We've folded it in half like that. Now, what you should be able to do after this is to look on the other side and find our original corners of our piece of square paper, and find the little sort of openings here. And what you can do is you can put your fingers inside there, and the same on this side. So those little openings there. And very gently, you can form something that looks a bit like a star. So I'll do that step again. So you've got your second corners folded into the middle. You fold it in half like that. And then you find on the outside where the little extra sort of pocket is there. There should be one on each side. Slip your finger and thumb in there. Do the same as the other one. And what you end up with is this. Now, you may have seen these before. This is what we used to make at school before we were allowed phones in the classroom. This is called a paper fortune teller, right? And it's got these little hinges, thanks to paper's amazing property of being able to be folded. It's got these little hinges. And what we're going to do with this is use it to choose what presents we're going to give to our friends and family this winter. Okay, so I hope that you've all got something like this. Mine looks quite ugly. Here's one that I made earlier, which is slightly neater. Mine's got a little bit creased. So what I'd like you to do now is to grab a pen or a pencil or something to write with. And we're going to make our gift selector, our paper gift selector together now. So firstly, if you've got your pen or your pencil with you, I would like you to take these four corners of your gift selector, and I'd like you to write on each one the name of somebody that you are planning to give a gift to this winter. Okay, so a name of friends or family members who you are planning to give a present to. I'm going to do it along with you. Still haven't bought anything for my brother yet. Okay, so you've got four names on there. And next, I want you to open it up and see these sort of inside surfaces now. There's 8 of them, because you can have 4 that way and then 4 that way. So there's 8 of those inside triangles. And on each of those triangles, I want you to write a number. It doesn't have to be number 1 to 8, but make them relatively low numbers. I'm going to do 1 to 8, but you could do anything sort of less than 20. So write those with a pen like that on each of those inside triangle surfaces. Okay, so mine looks like this. It's got number 1 to 8 all the way around. And then the final step of making your fortune teller gift selector is to open it up, and on each of these 8 inside surfaces, I want you to see if you could think up 8 different gifts that you could feasibly make for someone. So think about things that you can make at home. It could be maybe a cake or some cookies, or maybe you could make them one of these fortune tellers out of paper. Maybe you've always wanted to take up knitting. Maybe you could knit somebody a Christmas hat. Maybe you could write them something. Maybe you could write them a story or a poem or a letter or a card. Maybe you can make them a card. Maybe you could do a drawing. I want you to think of 8 different things that you could feasibly make for somebody as a gift. Because one of the things that I would like for you to take away from this, apart from that material science is awesome, is that as material scientists, what we do a lot is we think about sustainability of stuff. Lots of us have been thinking recently, I know, about plastics and the sustainability of plastics and how single-use plastics are polluting our environment and getting into the oceans and wreaking havoc all over the world, causing litter and microplastics and all of those sort of really damaging things about plastics. What we do as material scientists is we look at stuff like that and we try and find better solutions for it. And one of the ways to do that is to change the materials in a lab, make new materials, like I said, that we sometimes do. But another way to do that is to really redesign how we live, change how we live and be more sustainable. And there are lots of ways for us to do that. But one of those ways is to buy less stuff, get less stuff into our lives. And so repurposing, reusing stuff, recycling things, making things from other materials rather than buying them in a shop is one really good way to be more sustainable in how we live. So I would really encourage you, if you're planning on giving gifts this month, I would really encourage you to think about if there are any that you could make for your recipients, because that will be one small way of kind of tackling the problem of just all of the stuff that we have on this planet, all of the stuff that we're constantly making. So if you've got your 8 things that you could make, things that you could write, things that you could bake, write them down on here. I'm going to do a little list of 8 quickly. And then fold your paper back up. And there you have your handmade gift selector. So the way to play, hang on, let me get my slightly neater one. The way to play is to pick a recipient. So I'm going to choose my dad because I haven't got him a present yet either. And the number of letters that are in the word dad, so 3, you go like this: 1, 2, 3. So if it was my brother Matt, that's got 4 letters. So I'd go 1, 2, 3, 4. And whichever side you land on, be it that one or that one, next you have to choose a number. So I'm going to choose number 5. So then you go 1, 2, 3, 4, 5. And then you choose a final number. I'm going to choose number 7. And under number 7 is a poem. So I'm going to write my dad a poem next week. And that is a gift that has a lot of thought into it. That's the thing, when you make things for people, it takes a lot more time than just ordering something off of Amazon. And it has the double benefit of being sustainable and also of being kind of more thoughtful than just something off of Amazon. So I hope that that's useful. What we've done is we've used our knowledge of materials and material science and how paper is made up of cellulose, and it's got hydrogen bonds in it, which we break when we rip and when we fold paper. And we can use that material knowledge to make something like even as simple as this. And so that's an insight really into how material scientists view the world. And yeah, I hope that that's fun and interesting for you guys. I've got a couple more minutes now to take some questions. So if you've got any questions at all about material science as a subject, about how to get into it, about me or my career, how I got into material science, then do put them in the chat now, and I'll be really happy to answer them.
Awesome. Thanks very much, Anna. I've got my camera's working again, so
oh, hello. Hi, Chris.
Hello. How are you? How you doing? No, that was great. I mean, it's amazing all this material science behind just the humble piece of paper, isn't it?
Yeah,
it really is, because it's often sort of you hear the sort of number of times paper can be recycled as well, and as you're sort of saying, paper's got memory, and that's sort of
yeah, it's so true. Although it can't be recycled as much as something like glass, because you know, we looked at those hydrogen bonds. Those bonds over time will break down, so the fibers get weaker and weaker and smaller. So I reckon, I don't know what you think about this something like this egg box, which is made up of recycled paper, that's probably been recycled once or twice, and then any more than that, and I think it gets too weak, and so it can't be recycled anymore, or you have to mix in new stuff.
Has anyone got any questions for Anna? But no, with all these sort of technical issues, I didn't quite manage to get to the end of making. I managed to make it sort of like a table. I got to the table stage.
Excellent.
But I think Becky managed to do one as well. So if people have got sort of like did manage to make one, please share your pictures with us.
Yeah, definitely.
Oh, one from Matt. What's been the best handmade gift you've received?
Oh, that's a good question. The best handmade gift I've ever received. Well, I don't actually know if I've ever received a handmade gift. I'm trying to think. I got really into knitting a couple of years ago, and so I've given a lot more handmade gifts than I've ever received. So I've given last winter I gave loads of my friends for like birthdays and stuff, handmade knitted hats, like woolly hats. And I gave them all to my family as well. So there was a time when we were all walking around in like matching knitted hats.
Oh, fantastic. Oh, awesome. Anyone else got any? But no, it's also sort of that sort of selector that you made. It's a great one for the indecisive as well. Helps people.
Oh my gosh, I know, right? I'm so indecisive. Awesome. I guess if there's no specific questions, then maybe we can talk a bit about how to get into material science, because when I was at school, I had never really heard of material science. So already everyone watching this is way ahead of me when I was at school. And yeah, it's a course that is run by how many universities in the UK now? In the Discover Materials group, we've got 10 universities who are running courses or have got departments, but there are other universities that do run material science and engineering courses. Yeah, a kind of more than a handful, but still not so many universities that will offer it as a course to study. And yeah, it's still it's increasingly more mainstream, but it's still a relatively unknown subject. So it's brilliant that people like Chris are kind of shouting about it. But yeah, so the way to get into it is either through doing a university course in material science or through what's it called? Apprenticeship routes. That's it. So lots of companies now will offer sort of big engineering firms are increasingly offering apprenticeships as routes to get into being an engineer, and they're increasingly sort of well regarded and seen as kind of equivalent to a degree now, and so you can leave school and go and start work immediately and start earning money and learn at the same time, and you're still studying and you're still learning, but you're learning on the job. Because I mean, what's great about it is just it is so applicable to everything, and the degrees are so varied. I mean, I was sort of talking to some year nines, I brought up like lists, and you go from like nuclear and engineering to bio and natural sciences. It's totally amazing. And that's one of the really brilliant things about it, I think, is the crossover between other subjects. So you know, people come into material science from being architects or designers or artists or chemists or physicists or engineers. You know, it's a real mixture of people from that. It kind of touches lots of different disciplines, and I know that yeah, it's got a real kind of crossover with artistic subjects as well as scientific subjects, which I think is quite unique.
Yeah, I mean, that's the great thing. It's sort of, you don't have to think of yourself as a scientist for material science to be applicable or to be interested in.
Yeah, definitely. Yeah, I've got friends who studied fine art and have now ended up as material scientists. And you know, people that work in museums who have to do conservation of materials. And there's so many interesting careers available. And it's not just, you know, I mean, sitting in a lab is brilliant, and you can do lab material science as well, but it's much more broad than that.
Yeah, it is awesome. But I mean, sort of like at school though, it's sort of, I know you've I've got a daughter at primary school, and they're doing material science, house material science, but
Oh, cool.
which is wonderful. But it seems to be sort of in secondary school when they sort of when you're sort of studying physics, chemistry and biology, that there are still material science in there, but it's not badged as material science.
Yeah, exactly. That's so true. And yeah, like, you know, in my degree course, we touched all the different sciences basically. So, you know, in order to understand why glass is transparent, you have to understand quantum mechanics and how, you know, what atoms are made of and how that interacts with light, but also a lot of chemistry in terms of like, why do certain elements mix together and make something like steel or brass, or, you know, alloys of different metals together. And yeah, like I said before, a lot of engineering. So why do we make stuff out of this stuff? What's the best material for the job? How can we process it to be as good as possible, and answer lots of really, really important questions about, you know, mostly how we can live more sustainably, or how we can, live better.
Yeah, it's that sort of sustainable and environmental angle, which sort of one example has been going from plastic straws to paper straws, whereas sort of plastic straws hold their shape really well, and by the end of your drink, paper straws gone all mushy. But
yeah, well, exactly, as we've seen today, like those hydrogen bonds won't last forever.
Well, no,
they don't even last for as long as a drink.
It's a tricky one. So
yeah,
it is that. But it's also sort of how to use materials as well. I mean, it's because we're going to sort of like see later when we look at sort of packaging, that plastic in itself isn't sort of an inherently bad material. It's wonderful, but it's just sort of how it's used. And
exactly. And that's what's really interesting, is like how materials and engineering interfaces with human behavior. And, you know, why don't we want to get away from single-use plastics? What is it about the usefulness or the ease of it that means that we keep going back to it, even though we know that it's bad for the environment? And yeah, so the way that it interfaces with society and what we think is good and bad as human beings, it's all tied into why we do material science and the outcomes of material science.
It's wonderful. But so any other questions at all? If not, I'd like to sort of, Anna, thank you so much for your time, and this was a fantastic session.
No problem at all. Thank you for having me. And yeah, I wish everybody luck with their materials adventures.
Awesome.
Keep asking questions.
Thanks very much. And then it's also sort of like early next year, we'll be launching our new look website, where there'll be like loads more info,
awesome.
Routes into material science, and
very
people
cool
in materials. So it should be good once it's up and running. But no,
thanks everyone.
Thank you very much.
Bye.
Bye. So no, that was a fantastic.